Okay, this screencast is on the binomial expansion, and we start off by just defining what a binomial is. As you can see here on the screen, a binomial is a two-term expression, as simple as that. Any algebraic expression with two terms in it, binomial, bi by 2, you get it. The binomial expansion is dealing with taking that binomial expression and raising it to a power. So something like x plus 1 squared, 2x plus 1 to the power of 12. That's what a binomial expansion is concerned with, right? So we've been doing these sort of expansions, power 2 expansions, for years. So there's nothing mysterious about that. So what we're doing here is developing the skills and the understanding of an expansion such that we're going to be able to expand much higher powered binomials. Alright, so this is the target here. This became the sort of target of the lesson. These are the notes from the lesson earlier today. Just thought I'd put it into explanatory format into a YouTube. So, alright, this is the target. Excuse me. So the development of this idea comes from taking just your general binomial a plus b. A and b can represent anything, and then just having a look at increasing powers and seeing what results. Now, this is really what mathematicians do with everything. You start with the most basic of ideas, and you try and spot patterns and see what's going on, and see if you can therefore take those patterns, and if they work right across the board, then you can take those patterns to the nth degree, which literally is what we do. So looking at this binomial a plus b and then raising it to the power of 0, anything to the 0 is 1, so the result there is 1. That's quite a trivial one. Moving on, a plus b to the power of 1 is a plus b. And what we started to do was just note down what the coefficients were of a and b. So in our power 1 expansion, there's just two terms, a plus b, and the coefficients are 1 and 1. So we start to note these coefficients over here. And then we go to a plus b squared. In red, we're starting to just note the coefficients. A squared plus 2ab plus b squared. That's the expansion. A squared plus 2ab plus b squared. So each row of coefficients here turns out to be excuse me, what we know to be Pascal's triangle. French mathematician Blaise Pascal lived in the 1600s, I believe. Did a whole lot of stuff. He was very prolific, which you have to be really to have a triangle named after you. But so he came up with this nice patterned triangle, and the coefficients of all our expansions are represented in this triangle. So we get down as far as cubed, and we can do that quite easily ourselves. But then when it gets down to 4, 5, 6, these expansions become very time consuming. So we're now going to use the triangle to help us with the expansion. So we can see what the pattern here is, and just to reiterate, each number in Pascal's triangle sits in between two numbers above, and it's the sum of those two numbers. Right, so if we were going to the fifth row here, we'd take 4 plus 6, and that would be 10, 6 plus 4, 10 under there, 4 plus 1, 5 there. Right, always 1s on the ends, and if you look at it, it's palindromic. 1, 5, 10, 10, 5, 1, 1, 5, 10, 10, 5. Reads the same forwards and backwards. It's lovely. The first number in is always the number of the power that you're looking at, so the 3 there, the 3 there, etc. Loads of patterns. Okay, so what we then needed to establish was, okay, well, I get this situation, and we've got a power here, and whatever that is, whatever that value of that is, I've got one more term than that in the expansion, so a power 4 has got 5 terms. And if we pull out the coefficients, they make this nice Pascal's triangle. But the other thing to note is that the powers of a, in this instance, descend from a to the power 4, a to the power 3, a squared, a to the power 1, a to the power 0. So in each term, we have three things going on. One is the coefficients, which are in Pascal's triangle. 2 are the powers of this term, this a term, which start at 4, which start at that value there, and descend by 1 each time down to 0. And then the power of the other term, b, which starts at 0. There's a b to the 0 in there, but you can't see it. B to the 0. You can't see it because I didn't write it. And I didn't write it because b to the 0 is 1. Right, so I just remove that now because don't really want that in there. Okay, so b starts at 0, goes up, you see, goes up to 1, goes up 2, 3, 4, And another thing to notice here is the sums of the powers are always 1, 2, 2, 1, 3, 4, 0. Okay, so there's three things to sort of note in any expansion. So what we want to do though is, okay, the target was to get this power 12 sorted out. How do we do that? Well, I can either do 12 lines of my triangle here, which is going to take a huge amount of a huge physical effort in terms of taking up a lot of space, or I can look for a pattern. Now there's thankfully a pattern. These numbers are arrived at using NCR notation. So this fifth row, this is called the fifth row because of this number 5. This is the fifth row. All right, now we can find each term in the fifth row by calculating, in this case, the fifth row. This is the first term, or first position, maybe I should use first position. And well, your first thing you're going to say is, hang on, that's not the first position, is it? Because that guy there is the first position, but that is the 0 position. Come on, that's a 0 position. Everyone knows that. So 0 in the first position. 1, 2, 3, 4, 5. And so if this is fifth row first position, the calculation of that particular value is 5C1. Right, and I'm going to write that as 5,1 like that. Okay, and you guys know how to find 5C1. This one here, therefore, would be what? 5C0, C1, C2, 5C2. Let's just check if that's the case. Go into your calculator and bring up, right, it's menu 5, 3, 5, 2. Right, that's the fifth row, and the second position, which is actually the third number along, and hit enter. That's a 10. Perfect. 5C2 is a 10. 5C3 is also a 10. And away we go there, finishing with 5C5. Hey mate, you're up? Okay, excuse me, I just had a visitor to the room. Okay, so this now enables us to find out the values of these coefficients along any row. So if we go to the 12th row, rather than writing it all out, these are the values along our 12th row. 12 0, 12 1, 12 2, 12 3. So we could write out the 12th row of Pascal's triangle. We know that 12 0 1. We know that 12 1 is 12. 12 2 I'm not so sure about, so I could go in here and I could either go menu 5 3 or I could just hit NCR. I can just go to my keypad here and hit NCR, open up a bracket. It's a bit painful. 12, 2. Not sure I'll do that again. Hit enter. And that's 66, so I'll go back in here, that's 66 there, then I could do the same for 12C3. These calculators are a bit, but if you arrow up and hit enter, that copies it down, and then we can go delete, and put a 3 in there, and then we get 220, so that's our 220 position. So what we're doing here is we're coming up with the 12th row of Pascal's triangle using our NCR notation. Okay, so moving along, our expansion of, so a general way of expressing the expansion of a plus b to the power of n is like so. N being obviously anything, n0, a to the n plus n1, a to the n minus 1. So you can see that my powers of n are reducing by 1, my powers of b are increasing by 1. So b is going to go from 1 to 2 all the way up to n, whatever it is. He's going to start as power n and reduce all the way back to 0. And that's our full expansion of a plus b to the power of n. So we then started to just have a look at our task, which was sort of arbitrarily put up as 2x plus 1 to the power of 12, and the first few terms of it would be, this is my power, 12, 0, 2x to the power of 12, 1 to the power of 0. So when we go through this is 1, but then I need to pull these brackets out, I need to raise 2 to the power of 12, which is 4096. X to the power of 12, and so it goes on. Okay, I've left you with some homework. I'm going to do one of the questions in the homework. So I think I've left you with A and B from question 1. So if I do question 1D, which is saying this is expand each of the following is the binomial theorem, the binomial expansion. So I need to expand 2x plus 3 to the power of 6. Alright, and what I do there is write all this out, 6, 0. 2x to the power of 6, 3 to the power of 0. Now that's just 1, so I didn't really need to write that. 6, 1. 2x to the power of 5, 3 to the power of 2. Okay, so 2a, that's my a and that's my b. You see how this is working out. Plus 6, 2, 2x to the power of 4, 3 cubed. And you can see my powers are always adding up to, 654. See, that's incorrect, isn't it? I'm sorry, I've made an error there. That's a 1. That's a 2. It's a good job I was checking there. My powers always have to add up to 6 in each case. Alright, and we keep going for 6, 3, 2x to the power of 3, 3 cubed, and you keep going. So I'll just do the first few for you. 6, 0 is 1, 2 to the power of 6 is 64, 3 to the power of 0 is 1. So I've got this 1, I've got a 2 to the power of 6 and 1 there, so the whole thing is 64, x to the power of 6. This here is 6, 2 to the power of 5 is 32, times 3. So in my calculator, for this second term, I know that 6, 1 is 0. I'm just going to put 6 in for that. What was it multiplied by? 6 times 2 to the power of 5. 2 to the power of 5, I know that's 32, times 3. And then I hit enter, I've got 576. So I can put in here 576 x to the power of 5. Now 6c2, I'm going to need some help with that. 6c2, menu 3, no, that's incorrect. Menu 5, 3 is 6, 2. Hit enter. I've got 15. Now hit times that by, what am I timesing it by? 15 is 62. 2 to the 4, which is 16 times 9. 16, 2 to the 4, times 3 squared, which is 9. So I get 2,160. 2,160 x to the power of 4. Alright, I'll just do this last one. 6, 3. It's not the last one, but it's the last one I'm going to do. Menu 5, 3, 6, 3. Right, that's my NCR, 6, 3. I'm going to times that by 2 to the power of 3, then 3 to the power of 3. 2 to the power of 3 is 8. 3 to the power of 3 is 27. And I've got 4,320. 4,320 x cubed. Right, and I'll just keep going there until I've got all those terms done. So that's question 1. Question 2, I think I got you to do A and B. I'm going to have a look at, for you, question E. Question 2E, just to explain it really. X plus 3 to the power of 12. We want the 8th term. We want the 8th term. Now this means that that's the first, second, third, fourth. So we want the 8th term. We're not going to write all these out. We're just going to identify the 8th term. So if we started to write these out, we would have the first term is 12, 0, x to the 12, 3 to the 0. Right? Second term is 12, 1, x to the 11, 3 to the power 1. So what's my 8th term going to be? So my first, my second, my 8th term is going to be 12, 7, isn't it? 12, 7. So sorry, I should put a dot, dot, dot in there because that's not the next term. Dot, dot, dot. This is my 8th term here, 12, 7. Right, because that's the first, that's the second. Now what's my x power going to be? It's going to be, if it starts at 12, 11, what's that going to be? That's going to be a 5 there, is it not? Because that plus that has to equal that. 1 plus 11 is 12, 0 plus 12 is 12, so x to the 5, 3. Now these two have to add up to 12, so it'll be x to the 5, 3 to the 7. So for me, the 8th term is this, 12c7 times 3 to the power of 7, x to the 5. So I'll go to the calculator and work out what 12c7 is at menu 5, 3. I punch in 12, 7. Okay, I'm going to hit equals there, and then I'm going to multiply that by, I've forgotten what I said, 3 to the power of 7. 3 to the power of 7, this is a large number. Hit enter, 1,732,104. So that is 1, 732, was it 104? 732, 104, yes, 104 x to the power of 5. That is the 8th term. So we just went through and we worked out the pattern, and we worked out that that had to be the 8th term there, and so that is the only one we need to represent there in our answer. So that's how to do that. Okay, I'll leave it at that. I'll see you in class on Thursday.